I'd like to welcome everyone to the 57th annual Jansky Lecture. This is, of course, the first one we've had for a few years face-to-face after a couple of years of COVID. This is a distinguished lecture series established by the trustees of Associated Universities, Inc. and the National Radio Astronomy Observatory to recognise outstanding contributions to the advancement of radio astronomy. This lecture series is named after Carl Jansky, who was the first person to detect radio waves in 1932. And we have a member of the Jansky family in the audience here, David Jansky, his son. Where is David? So tonight's lecture is Symbiosis Between Black Holes and Galaxies by Professor Francoise Combes. She is being honoured for her significant contributions to the field of galaxy formation and evolution, the interstellar medium, dark matter, and radio astronomy in general. Her expertise in a wide range of fields over the course of an outstanding scientific career has extended her influence to the entire breadth of astronomy. She received a PhD in astrophysics from the École Normale Supérieure in Paris, and she is currently a professor at the Collège de France, and she's the chair of the Galaxies and Cosmology Department. She's authored over 1,200 publications and more than 20 books. Her work has been recognised by numerous honours and awards, including the gold medal from the French National Centre for Scientific Research, a fellowship in the American Astronomical Society, the Tycho Brahe Prize from the European Astronomical Society, the L'Oréal UNESCO International Award for Women in Science in Europe, and an honorary fellowship of the Royal Astronomical Society. Beyond her scientific contributions, she has an incredible history of contribution to our field more generally. She is the Vice President of the French Science Academy. She has been the President of the French National Astrophysical Society. She is the long-time scientific editor of Astronomy and Astrophysics, which is one of the premier journals in our field. And she had, for many years, key advisory roles in the Atacama Large Millimetre and Submillimetre Array, in the Square Kilometre Array project, which is being built, the Hubble Space Telescope, and roles in the International Astronomical Union. So we are incredibly proud and delighted to have a scientist of her stature, and please join me in welcoming her to Charlottesville and the lecture series.
So thank you very much indeed. I am very honored and really very happy to be there. And today we'll speak about the impact of black holes on galaxies. So I will try to share with you all the progress that we have made recently with the black holes. You know that black holes, astronomers did not believe in the existence of black holes until 1965, so it's a relatively recent domain, and you have seen all that recently in 2019 there has been a breakthrough, in fact, by the EHT, which is the Event Horizon Telescope, that were able to make the image of the shadow of a black hole. So the shadow of a black hole is this. You see a ring of emission, which is synchrotron emission of charged particle in the magnetic field. And this gas is ionized gas, which is rotating around the black hole. And you have a hole, a black hole, really. And this is due to the fact that all the photons are swallowed by the black hole. There's a lot of photons, in fact, but you don't see anything because there is this famous shadow. This shadow is a function of the horizon, where the escape velocity from this object is larger than the velocity of light. So the light cannot escape, and that's why it's a black hole. And how this breakthrough has been possible, in fact, it is by a VLBI, the Very Long Baseline Interferometry, with a wavelength of 1 millimeter. And this is from a telescope in Europe, in the States, in Chile, and even in the South Pole. And they are using the diameter of the Earth, 12,000 kilometers, to have the baseline and to have a resolution of 20 microarcsecond. Of course, this VLBI was known for decades, but in centimeter wavelength. And you see here some of the images that you can have. You see the different sizes here, 4,000 light years with the VLA here. And you have the jet. It is M87, the galaxy, the central galaxy of the Virgo cluster. You have the jet, and the jet is coming towards you, so it's boosted here, and you have the radio lobes. You have also this synchrotron emission is still visible in the optical. You have this Hubble Space Telescope, the jet, and when you have the VLBA, a very long baseline, you have 0.1 light year, and you begin to see the jet is coming in two parts. And of course, you need to have a jump here, 1 light week instead of 0.1 light year, and to see this, this shadow, and this is because you are mounting in frequency, and it is a challenge because at 1 millimeter the atmosphere is not so stable, it's not so transparent as in centimeter, so you have turbulence and you have a seeing and problem and so on. So this remarkable discovery is really a challenge in a range of scales that are explored. Here you see in the Virgo cluster, you have M87, the main galaxy of the cluster. You see the shadow of the, this image, which is 80,000 light years. Here you have the jet, which is completely asymmetric because M87 is moving. You have a zoom here, and you see the different zoom with the jet and jet becoming in two parts, and finally the shadow of the black hole. But look, it's 0.115 light years, so you have 7 orders of magnitude. It's really spectacular, and all this, the size of the shadow here is giving you the mass of the black hole. It's a giant black hole of 6 billion solar mass. And we'll see that the shadow will bring also other information. So why in 2019 they have not done first the image of our own black hole in the galaxy, because it's the best known black hole. It is very close. It's only 27,000 light years away, and they could have done it, in fact. And instead of 1 light they have 1 AU. 1 AU is astronomical unit, that is the distance between Earth and Sun, which is 8 minutes in light distance. And here, why? In fact, you see that M87, it is at 60,000 millions light years, and it is 2,000 times more farther than the black hole in our own galaxy. But the black hole in our own galaxy is a very small one. It's 4 million solar mass only. So there is, by coincidence, about the same ratio between the mass and the distance, so that since the horizon and the shadow radius is proportional to the mass of the black hole, you have a compensation between the distance and the mass, and finally you expect the same angular distance, the same size in the sky. So they could have done it even before M87. So why was it so difficult? In fact, because the period of rotation of the gas, of course, it's also proportional to m. You can compute it by the Kepler law. And then if a rotation in Sagittarius A star, which is the black hole of our own galaxy, is only about 30 minutes, for M87 it's 50 days. So M87 is very stable. When they observed in April 2017, they can integrate even several days. It's exactly the same. Here you have a simulation. It's exactly the same shape, and they can stack all the image and have coherent things. While for Sagittarius A star, you have clouds falling in and rotating around, and finally making a bump and then no bump and so on. You see the variation here. And you have something which is not coherent. So they made a lot of time to finally stack a lot of these very variable images and thousands of simulations. And at the end, in 2022, came out this image of Sagittarius A star, and you have seen that maybe, and it is really the same size, in angular size, as expected, because, and they have also microarc-second resolution, and the size of the shadow is 0.2 AU, much smaller, but in size it's the same. So I want also to point out that it's not only radioastronomy, although we are focused on radioastronomy today here, but there is also at the same year, about 2018, the results of gravity. Gravity is an instrument which is on the VLT, the Very Large Telescope in Chile, from ESO. There is 4 8-meter that can be combined to make a VLTI, VLT interferometer, and they have about the same spatial resolution, 20 microarc second. Why? Because even if they have only 100 or 200 meter baseline, they have a wavelength which is 2 micron in the near infrared, and these 2 microns make the difference, so it can have the same resolution. They cannot do images like in radioastronomy because the atmosphere is too turbulent, but they can follow the flare of Sagittarius A star, so points, and it is rotating like that with a red velocity, blue velocity, and the size of the ring is about the same. It's almost face on, and they found exactly coherent results with the radioastronomy. So here you see that we are very proud to see this at last image of the black hole, but it's still a little blurry. We want more. We are never satisfied as astronomers, so we want something more smart. And here are simulations that we could do with a new generation EHT, new generation Event Horizon Telescope. Why you can have more sensitivity and more resolution? First, you could go to higher frequency, maybe 0.8 millimeter. You can also have an instrument in space to have more baseline. You can have more telescope to have more sensitivity. So all this is possible, and here is a simulation that could be done in the future at 1 millimeter, 3 millimeter. And the difference is that first you see with more thin details the ring, and you can measure some special distances. And you can also have the jet, because you have seen at large scale, we see the jet, but for the moment we have only seen the shadow of the black hole. So here we expect to see the jet, and it's very important because for the moment there are a lot of theories. What is the origin of the jet? Is it the disk? Is it magnetic hydrodynamics that make this jet? Is it the wind? Is it several things that we could solve by having these images? So here are exactly the importance of the model. Here you have a model making this emission, a synchrotron emission. Here is the model that you have smoothed out to have the EHT resolution. You see that it is indeed blurred and it corresponds to the observation. Here you have a linear scale, and here you have a scale, gamma scale, that allows to see the low surface brightness image. So what we want to see is that. And the main thing is that this size is function of the spin of the black hole. And the spin of the black hole is very important to know how the black hole has been formed, why it has kept some angular momentum. And the spin of the black hole is also important to when the black hole spin. Of course, the black hole makes the gravity, which is not a force like electromagnetism, it's a force that makes a deformation of space. So when there is a spin, all the space is rotating and is entraining the gas in its rotation. And when you compute the rings of the gas, there is an innermost stable circular orbit, the last orbit stable, and inside the gas is drawn to the black hole. So it's important to see that because it's what you see in the orange ring here. And the same for the photons. The photons are deflected by the mass, and it's like a lensing because of the deflection of light by the mass. And then you have also a photon ring. So what is shown here is in the, you don't see very much, but there is in the horizontal scale something proportional to the spin without dimension. So you have 0 and 1, 0 rotation, 1 maximum rotation. And you see that this, the stable innermost circular orbit for the gas is going down. So the gas is able to go very close to the black hole if it is rotating in the same sense as the spin of the black hole. And why, if it is retrograde, it is the reverse. And for the photon ring, is the same. So all this, if you can measure this photon ring and so on, you see you cannot still measure it because it's too blurred. But then you will be able to have the exact spin of the black hole, and it is why it is very important to go further and to do some progress still. And here, for the simulation there, it was possible to see that both black holes, our own galaxy and M87, are rotating, but we don't know how much. There is a big error bars. So what also there's a lot of progress here is, for instance, at low frequency, there is now a LOFAR, low frequency array, in Europe, in Netherlands and France and so on, which are able to see low surface brightness emission. You recognize here the jet that we have already shown in the previous slides. And at low frequency, the index of the synchrotron is very steep. So at low frequency, you have more emission. And it was possible to see with LOFAR all these radio lobes. You see all this that we have already shown, all the zoom in until the image of the black hole. And for the Event Horizon Telescope, they have not done only M87 and Sagittarius A star, but a lot of nearby active galactic nuclei. For instance, Centaurus A. It is a black hole which is 6⁻⁷ solar mass, so 100 times lower than M87. So even if it is closer to M87, you don't see the image of the shadow of the black hole. It is 100 times smaller. So you cannot see, but you see the jet, the reverse. So it's very interesting. The jet is not unique. It's like a polar cone, and you see the edges of it. It seems to be normal. Even in Perseus A, you see also this kind of shape. And I will also show this beautiful blazar. A blazar is what? It's a quasar, active galactic nuclei, very powerful. And the jet is coming towards you, so you have a boost of the Doppler effect coming towards you. And here you have only one jet that you see, the counter jet you don't see. And here you see the progress that has been done with time with a resolution. So resolution is the key here. You see 150 microarc second first in this first image, in 1217 here. You have a core and you have the jet. When you make a zoom, where this square in white is this square here, you still find the same direction, which is not obvious here because of the beam here. But here you have again a core and a jet with 50 microarc second. When you look at the 20 microarc second of the Event Horizon Telescope, then, surprise, you find that you have not the same direction as usual, but you have something perpendicular, meaning that something happens very close to the black hole. Maybe you have precession, and this is very interesting because we want to know what is really happening to the black hole. This quasar is at a redshift, a distance rather far, 0.5, and mass of this black hole is 8 to the 10 to the 8. And this is a well-known blazar, in fact, 3C279. It is known to have superluminal velocity. What is superluminal? That is, it is apparently going faster than light. Here you see that is known for a long time. It was observed in 1992, for instance. And you have here 6 years. And you just look at the relative distance between two clumps. And you see that it has run 60 light years in 6 years. So it is apparent velocity of 10 times the velocity of light. So why? Of course, it is not, it is only an illusion. And why is there is this illusion? It is because when you have this clump coming towards you, it is in advance with respect to this one, which is farther away. And when you receive this signal, it looks like it is coming too early because the other one has a delay. The delay is the light, is the time that the light comes to make this, which can look very small distance, but the messenger here is running at about the same velocity as the clamp. In fact, the clamp is almost the velocity of light, and because this is in advance, you have the impression that it is more than velocity of light. So this is interesting. But now let's look at what we see with the Event Horizon Telescope. Here you have seen that there is a perpendicular things, and since we can see the proper motion, we see that all the jet is going in this direction as we expect, but this one is going there. So indeed, there is something strange, and certainly it is precessing and maybe changing orientation, and the velocities here are about 15 or 20 times the velocity of light in apparent velocity. You have a lot of resolution here. So another continuation on this same blazar, you have seen here with the EHT these two perpendicular things, and now we have also, you can compare with the Radio Astron, which was a space VLBI, with now a baseline of 300,000 kilometers, and with 22 gigahertz, that's 1 centimeter. And then you see in blue the contours, which are the low resolution here, and we see that there are a lot of details. You have more sensitivity here, you have a lot of details, and you have filaments here. You can even measure the polarization, that is the direction of the electric field, so you can measure the magnetic field. So you can be doing some physics here to know how these jets are running. And here is the interpretation. You have, for instance, 3 filaments, and interpreted by instabilities like Kelvin-Helmholtz instabilities. A very nice resolution, and almost you can compare with some simulations here. And certainly it has to do with the precession due to the spin of the black hole. You see here some simulation where the black hole spin tends to align, it torques the gas which is falling in with a different angular momentum, and it is falling there with filaments with certain disorder and random, and we are just able now to come to the physical mechanism that were simulated but never seen. So this is really a very impressive result due to high resolution in radio astronomy. So now I will come back a little bit in what I wanted to do with resolution, high resolution with ALMA to some close to the black hole. And I want to first describe the view of the paradigm that has for years been the proposed theory to interpret what we see in type 1 and type 2 AGN, active galactic nuclei. So you have here the typical schematic view. You have a black hole here, you have an accretion disk that we have seen rotating by 100,000 kilometers per second, 1/3 of velocity of light, accretion disk, and then you have some region which is rotating a little fast also, 10 or 20 kilometers per second, because we are close to the black hole, and we call this region broad line region because it's widened by the velocity rotation. And then you have what we call an obscuring torus, and very thick torus. Why? Why we need that? We don't know if it exists or not, but it's just a model. Why? Because we think that we see two types of active nuclei, and they are the same objects, but seen by different orientation. So if you look at the observer's layer, you see the broadline region because they were not obscured. And if the observer is here, you will be obscured by the torus, and you will see only the narrow line region. Narrow line means that it will be farther from the black hole, and it is illuminated and excited by the black hole, and certainly is due to the feedback of the black hole, that is the wind of the ejected gas. So given the similar abundance of type 1 and type 2, you need to obscure a lot. That's why this was very thick. But finally, I will show you that nowadays we are more shifting the paradigm to some view which is less thick. In fact, we have seen with ALMA this kind of molecular disk, which are thin disk, and looking at molecule like CO, which is a tracer of H2. We have also maser of H2O, we have H2 in the near infrared. So all this molecular disk, or molecular torus, maybe, by analogy. And then you have the black hole and the big blue bump, which is the accretion disk, the broad line region. And you see that close to the black hole, it's too hot and too hard radiation that all the dust is sublimated. So you destroy the dust until a radius of what we call a sublimation radius, that or the near infrared is not emitting anymore. And we have seen that with the interferometer, with the VLT. We have mid-infrared interferometer, MIDI, Matisse, and instruments like that. And we have been able to have this image, the resolution with the dust. So the dust, by the energy pushed by the active nucleus, is pushing the gas, and you have a polar cone with hollow cone because you have all the gas. And all this, the dust is extended. So finally, you don't need a thick torus. You need only a thin disk and a polar cone, and you have a large covering factor of the dust. So you obtain what you wanted, the type 1 and type 2 gas. So I will try to show you how we get to this kind of view with recent high-resolution observations. So my outline of this demonstration will be, first, we want to know how the AGN, the active galactic nucleus, is fed by the gas. And this is a problem in itself because there is a lot of angular momentum in the gas. The gas is rotating around the black hole. You have to get rid of all this angular momentum. And for this, you need torques. And to have torques, you need to have a non-axisymmetric distribution in the potential. And this is due to bars and nuclear bars and spirals. It is not axisymmetric, so you need torques due to that. So I will try to develop that. And also, the second point is what we have discovered in the recent years, a lot of molecular flows, which are, well, of course, ionized gas outflows were known for more time, but there are a very small amount of mass that is ejected. When you look at the molecules, it's 10 times more mass ejected. So we think that the energy of the AGN is able to push out the gas and to stop the star formation, to quench star formation. So we want to know if this is very efficient or not. And I will terminate by the molecular torus that we have discovered thanks to ALMA and high resolution. These molecular tori are decoupled from the rest of the galaxy. That is, they are not at the same orientation. They are about 10 parsec or 20 parsec, and they are completely warped. So, since I told you that we need bars and spirals, I just want to recall a few items due to bar. What is a bar? A bar is a density wave in a spiral galaxy. It's not a material arm, it's a density wave like spiral arms. And this bar is rotating constantly with radius, while all the matter is rotating differentially. That is, the matter is rotating very fast in the center and slow in the outer parts. And since you have not the same pattern speed, rotation, angular rotation, you have some resonances. And the bar here, when you look at the orbits of the stars, they are parallel to the bar. The bar is horizontal here, parallel, so they are supporting the bar. And at the end of the bar, you have a corrotation, a resonance of corrotation, that the matter is rotating at the same speed of the bar. And at each resonance, it has been shown that the orbits of the stars are changing by 90 degrees. So the orbits of the stars are 90 degrees with respect to the bar. And you can understand why the bar ends at its corrotation, because outside you have orbits that do not support the bar, they are completely perpendicular. And then you have another resonance that we call outer Lindblad resonance. There is two of this kind, inner and outer, and each time you change by 90 degrees. When you consider gas instead, of course the gas, a cloud of gas are colliding, so they cannot cross each other without being stopped. So for stars it's possible, there's never collision of any star. So you can have perpendicular orbits, but not the gas. So the gas, what it's doing is instead of, in each resonance, instead of rotating suddenly by 90 degrees, it turns gradually by 90 degrees, and it makes a spiral like this. And you have all these orbits that are precessing like that. And of course, at resonances, the gas is aligned to the bar. Here you see a galaxy, typical galaxy in the B minus V in the color. So you have a blue color in black here. And you see there is 3 rings, 1, 3, and 1, 2, 3. One, it is at the inner Lindblad resonance, one at co-rotation, and one at the outer Lindblad resonance. So why? Because the gas, when it is aligned with the bar, there is no torque, and it is piling up there and making stars. So how do we really feed the black hole? In fact, because sometimes you have resonance where you have a ring and you don't go, the gas don't go to the center. So what we need, in fact, is embedded structure, a big bar, and within the big bar, a small bar. And that's exactly what we see in simulations here. You have a simulation with stars, you have a big bar, and you have a second bar, which is not oriented at the same orientation, but also it's not rotating at the same speed. So it will never be in phase. In the gas, you have also this small ring and a spiral. And you see, to see where are these resonances, you have to plot this omega curve. Omega is the angular rotation of the galaxy. When you have a rotation curve, V of R, you have omega is equal V over R. So each time you measure the rotation speed, you can measure omega. And also you can combine with the kappa. Kappa is when you have an orbit at 0 order, which is circular. Kappa is a small epicycle around the circle, which is a small radial and azimuthal. And of course, these are the proper motion of the matter that resonate with the bar. So when you have a pattern speed of the bar here, you have here the co-rotation, you have the inner Lindblad resonance and the outer Lindblad resonance. So you can plot these 3, 1. And when the gas is coming to the center because of the bar torques, you make the mass increase in the center, all these curves increase in the center, and then you will have this decoupling of the secondary bar. And this is the secondary one that will provoke the feeding of the AGN. So if you want to know quickly and with some schematic drawing here, the action or the sense of the torque of the bar, you make this plot here. You have a bar, the spiral arms here, and the sense of rotation is this way. So you always, the matter enters always in the concave part of the spiral. And a bar is splitting the space in 4 quadrants. What are the sign of the quadrants is the sign of the torques. In fact, when you have the torque is due to the tangential force. The radial force makes a 0 torque. Okay, so the tangential force, how is it oriented? Of course, it is a force that restores the matter into the potential well of the bar, which is there. So it must be like this. And with respect to omega, you see that it is a positive torque. So you are giving angular momentum to the gas, and instead of the gas is not going down, it's going outside, and all this gas is making the ring at the OLR because it is driven outwards. But now, if you prolong this spiral inside the bar, which corresponds to the dust lane inside the bars here, then you see that you pass the spiral structure in the other quadrants, the 2 other quadrants, which are negative torque. So here the restoring force is always due to the potential wear of the bar, and then you have a negative torque this time. So all the gas from the bar, the co-rotation of the bar to the center, will go down. So this is what we want. All the gas will be driven to either the center or the inner Lindblad resonance. And how do you push it further to the center? It is because of secondary bar. So we are waiting. Well, first, how do you quantify this process? We want to know in which time the gas will go to the center. And then you can do that by computing the torques. How you can compute this? We can compute the potential of the galaxy. It is a disk, so you can take an image of the near-infrared, which is the old stars. Most of the potential is due to the old star. The young stars is a very small amount. The gas also is 5%. So you can take a near-infrared image with a Hubble Space Telescope, you deproject it, and then in each pixel, you resolve the Poisson equation, giving the potential as a function of density. And then you have these 4 quadrants that I described earlier, the positive in red and negative in blue. And of course, we want to know if the gas will be driven in. So you plot the contours of the gas with an interferometer like a NOEMA or ALMA, and then you see that all the gas is in the blue zone. So if you average over radius, you will have this kind of feature. This is the angular momentum loss, relative dl over L, the relative loss of angular momentum in one rotation. And you see it's negative, and it is 30%. So you lose each time 30% of angular momentum. In 3 rotations, all the gas will be in the center. So you have quantified by the observation the mechanism to feed the AGN. Now we have done this kind of computation for about 20 galaxies in a program with Santiago Garcia Murillo and others in the team. And at the resolution of NOEMA, IRAM interferometer, you have 1000 parsec. At this scale, we find only 1/3 of the galaxies that were in the process of feeding the active galactic nucleus. So it was not really smoking gun evidence of fueling the Cepheid galaxies that we're observing. Why? In fact, because, for instance, like this one, you have a bar, you have a ring, inner ring, and you see if you make a zoom here, you have all the gas stored at the inner invert resonance. So you have not yet another bar inside the bar to really push the gas to the center. Here you see what we are expecting here. You have a 3 snapshot of a simulation, large scale and a zoom in. And you see that at the beginning you have a gas stored in the ring, indeed. And after a while there is a nuclear bar, and finally all the gas is going to the center due to the action of the small bar. So you have to have like Russian dolls, a primary bar, secondary bar, and maybe a third bar, just to push the gas to the very center. Okay, so we wanted to see that because at IRAM interferometer we had not enough resolution to see what's happening after the first bar. So we did some project with ALMA in cycle 0 and cycle 1. And this is one of the images that we got. Here is a nice barred galaxy that you see here in a HST image with the ring of star formation, ring of gas at the inner invert resonance. You have the dust lane here, and so on. And the image is in blue, the HST, and in yellow and orange, you have the ALMA CO322 map that is tracing the H2, the molecules. And what we have observed in this galaxy is that there is not only one ring, but a second ring. So finally, the gas is not going to the center, but it is stored in a second ring, which can be the second inner invert resonance. And instead of being fed, there is also a small outflow that we saw in the minor axis. And it is very small outflow, maybe one of the smallest outflow of 100 kilometers per second, but still it is not fed. What is happening? We have computed here, well, you see here the deprojection of the CO molecular mass. You have the big ring here and the small ring here. We have also computed the torque map here, the red and blue quadrants, and when you make the relative angular momentum evolution, you see that it is positive and negative. So indeed, you are pushing the gas on the second ring that we see in ALMA. So it was not very demonstrative. This galaxy, again, is not fed at the resolution of ALMA. But this one was more promising. You see 1566, it's a nice bar galaxy with a spiral. And the field of view of ALMA in the band 7, CO322, is just 18 arc seconds. So we are just mapping this. And oh, surprise, there was, of course, this ring here, which is exactly at the field of view. So we see a very small intensity because of the beam, primary beam size. And then inside this ring, what we see is a nuclear disk and with a nuclear spiral that was not seen before. And you see also the velocity field, which is a little streaming motion due to this nuclear spiral. And the surprise here was that this nuclear spiral is trailing. Trailing meaning that the winding sense, you know, of these arms is the same as the big arms, which are trailing also. So you see here it's rotating like that, and the same things. So why it was a surprise? In fact, coming back to the orbits of the stars that I just described, we were expecting a leading, the other sense of rotation. Indeed, here I reproduce the orbits of the stars in the rotating frame of the bar. So you have first some orbits that are parallel to the bar, supporting the bar, and then you have co-rotation, you have only one epicycle, because it's rotates at the same speed, and then you have this perpendicular orbit at the OLR. And here I have the same thing but with color for the 4 quadrants. And you see that in this outside of the bar, for the gas streams, you have this trailing spiral structure expected because you are outside the bar. And then what is expectation? If you have no black hole, you expect to have a leading. You say here trailing and here's leading. If you have a black hole and the precessing rate of these different orbits is changing sign, that you have a trailing spiral structure. So the result is that because we are now entering, thanks to the ALMA resolution, on the sphere of influence of the black hole, then we change the process of precessing, and then we are able to see this configuration. And this is what I explained here. In fact, when the gas is coming in, first you have the gas which is the precessing rate is increasing, and when it is increasing, it takes in advance with respect to the rotation of the galaxy, so you have a trailing spiral structure. And when it is going down here, it is leading because, of course, it's precess in the other sense. Okay. And when there is a black hole, all the curves are back up again because you have a Kepler potential and all the omega is going to infinity if it was on 1 over r. But here, all this means that you have again trailing, leading, and trailing. And if you are in this zone of influence of the black hole, you have again a trailing spiral structure. So this is very surprising but important because now we know why the torque is negative and coming to the black hole. If you have a big black hole and you are inside its sphere of influence, then you can feed the nucleus. So here is the computation. We deproject the gas, we make the torque map also, again negative and positive, and you see that the spiral structure here is in the negative part of the torques. So when you compute the loss, relative loss in one rotation, you have a negative value here, and it's very strong. In 1 or 2 rotations, you have fed the black hole due to this spiral structure here. So here is the real velocity that you can have here. So this small nuclear spiral structure that were not seen before, we see in many galaxies. In fact, almost half of the galaxies that we have looked at, for instance, 613 or 1808, you see 1808 here. Here is a map in the CO322. You have the scale 50 parsec, and we see that also in the dense gas tracer, HCN 423 that you can see in the same time in the band 7, and the HCO plus also 423. You see this nuclear spiral structure really visible in the dense gas. So it's really meaningful for the density of the gas. You have the velocity and also the rotation curve that is boosted due to the black hole. And the resolution here was 80 milliarc seconds, meaning 4 parsec on the galaxy. So you are here indeed very close to the black hole. That's why we see different things. And I want to insist in this high resolution necessary to do this because, for instance, in this galaxy, there was some previous ALMA result by Miyamoto et al. With lower resolution. So you see the inner Limbrad resonance ring, but inside you see only a blob, while when you go far in the resolution, 60 millisecond or 5 parsec, then you see not only the ring, but also this S-shaped, which is a nuclear spiral, with also a velocity, which is almost a major axis blue and red in the east-west. Here you see a box of 10 arcsecond, and if you make a zoom by a factor 10, you have 1 arcsecond here. You see the S here, CO322 in contours, and inside this nuclear spiral, you have the continuum, the synchrotron continuum of the Seyfert, and at the same scale, you have also the HCO plus. So inside this nuclear spiral structure, you find a disk which is decoupled. You see the velocity is now north-south, blue and red north-south, instead of east-west. So you have a disk which is rotating, but at the different orientation and different kinematic axes. And that's what we call the molecular torus. The molecular torus is inside the nuclear spiral structure, and it is close to the closest molecules that we see to the black hole. And what happens for this warping, and why is it decoupled? Maybe it has something to do because its molecular torus is just outside the broadline region. Broadline region is up to 1 parsec, and then you have the accretion disk. And the accretion disk is warped due to the black hole spin that we have described at the beginning. So the black hole spin is warping because it is the gas which is accreted by the black hole has not the same angular momentum, and the torque due to the black hole spin is warping the disk. And you see this warping, for instance, in the H2O masers that is well known in NGC 4258. You have two possibilities in this schematic view. Is if the gas is viscous enough, all these torques make a warp like this. So we have a different orientation of this disk with respect to the large-scale disk. If the viscosity is not enough, you will have a split of a different radii. So you can have a split like this. And maybe this splitting will have more effect on the feeding of the black hole. I will describe later. So this lens stirring effect, which is the rotation of the referential frame that are around the black hole, is maybe the source of this warping and different orientation at near the black hole. So for this galaxy that we were describing here, we have also computed the torques and so on with different structure, the S-shaped and that's it, that are described here. And the relative loss of angular momentum is even larger in this nuclear region. Here, it is almost 100% in one rotation. So in one rotation, all the gas will be feeding the black hole. So we have at last find the smoking gun evidence of the feeding of the black hole. Now I speak to the feedback that I wanted to cover here. The feedback means that at the same time that you are feeding the black hole is so energetic that in the perpendicular direction it will push the gas up. So in the same galaxy, 613, we see both the feeding and the feedback. And the feedback is on the minor axis here. You see that the PV diagram, you have indeed some very high velocity. The main disk is there, but here you have a feedback which is even not resolved with ALMA. It is only resolved in velocity, and you have the blue and red part of the velocity here. And this direction is parallel to the VLA contours here. The jet, the radio jet in centimeter that you see is also parallel to the molecular jet, in fact. So we have some outflow of gas of 2 × 10⁶ solar mass and 15 solar mass per year. So it's able to push gas and prevent it to form stars to have a feedback effect. In this one, 1808, where we also see a nuclear spiral, so feeding of the black hole, there is no feedback at the black hole scale. There is no outer jet. It's surprising because this galaxy is well known to have galactic wind. In fact, you see dust lanes in the Hubble Space Telescope image, but it is a 100 parsec scale, sorry. And we think that this outflow is due to the starburst. There is a little starburst, and with a supernovae, you can also push the gas and make some feedback to stop the star formation. And there is always a question, is there feedback due to supernovae or to the AGN? And in this galaxy, it's, if you have enough resolution, you can tell that at 10 parsec, there is no feedback. So the AGN is not the culprit here, it's more the star formation. And we can really isolate the star formation and AGN because they have not at all the same excitation of the line. You have HCN over CS, or HCN over HCO plus, and it's well known that HCN is pumped by the hard radiation of the AGN. And in the red here, you have the AGN excitation, and we can separate with the resolution we have with the blue, which is the starburst region. So there are two phenomena, and sometimes when we have not enough resolution, we cannot separate the two. So for the AGN feedback, we have two mechanisms that still we don't know exactly which one dominates for the nearby active galactic nuclei. So either you have a very strong quasar mode, what you speak of, that is an AGN which has a high luminosity with respect to the maximum luminosity that we call Eddington luminosity when the radiation pressure, due to the high luminosity of the quasar, the radiation pressure pushes and compensates gravity, so you cannot accrete more. So this is a limit that the black hole can swallow gas because of its energy. It prevents the gravity to pull the gas in. So when you have a ratio of Eddington ratio here, which is close to 1, then you have radiation pressure, and of course all the gas is pushed back. So you have this kind of feedback. You have also feedback on the dust. And the second thing is all the Seyfert that we have around, in general, they have not very large luminosity, they are low luminosity AGN. Quasar is very rare. So when you have an Eddington ratio less than 1%, you have not enough radiation pressure to push the gas. So the only way is the radio mode, that is a radio jet. You have, we have seen radio jets in, around the black hole, and the radio jet can entrain gas and push gas away, even if you have not enough radiation pressure. So we have seen that this is indeed one of the main things in nearby Seyferts. For instance, 1068, which is the prototype of Seyfert 2. We have here a nice bar spiral. We have an inner Lindblad resonance ring, which is at 100 parsec scale. You see that the AGN is not in the center of this ring, so it's not at the center of gravity of the galaxy. It's wandering a little bit. It's not symmetric, but you have here, in this direction, a radio jet, well known in the centimeter. And it is exactly what we have in mind. This schematic view is that the AGN is not at the center of the ring here. And when you make an edge-on view, you have a jet which is pushing the gas in the plane of the galaxy. So it's a lot of coupling, the radio jet. Why? Because the radio jet is perpendicular to the accretion disk, which is decoupled from the rest of the disk. So we have not the same orientation. So we can push a lot of gas, and that's why there is about 63 solar mass per year ejected in this galaxy due to the radio jet. And here you see the power of ALMA here. You have the ring, the AGN is here, and when you make a zoom here, at the high frequency, CO625, so we have on band 9 now, and you see first a CO which is in the disk, and you begin to see the emission of the dust now the dust emitting like a black body or gray body, and then the dust is perpendicular. You see that it is in the polar direction. And why, when you see the CO2 to 1, it is really in this direction, which is perpendicular to the polar cone. And this polar cone is really visible very beautifully in the near-infrared of the sphere instrument on the VLT. And this image has been obtained in the polarization, so it's not the direct image, it's a polarization, and even when you make the non-axisymmetric part of this, and you see that there is indeed a molecular torus here, and a polar cone, that is, the dust is pushed in the perpendicular direction, and this near-infrared and ALMA view is completely coherent. So you have the molecular disk and the polar cone. This is known now for several AGN. Out of a sample of 150, they found 21 like this, where they are able to resolve the dust emission with the interferometer of the VLTI. And then you see that in 1068, for instance, the dust in the near-infrared is really in the perpendicular direction, and the green is the perpendicular direction, and indeed they are. So what we are expecting is to see a dusty torus. In fact, we see perpendicular emission. So it's a polar dust along the polar axis. And why? Of course, there is also some dust in the disk because there is molecules, but this disk is cold, while the outflow is more hot. And when you look at the near-infrared emission, you are focused to the hot dust, and the hot dust is more in the polar direction. So that's why we don't need the dusty torus of the paradigm. We need only the polar cone that obscure the Cepheid-2, and for 1068 there is indeed a column density of 10 to the 24 that is able to obscure the BLR. So we have seen also a lot of molecular outflows. This is one of the spectacular one. Here it's a galaxy which is lenticular. We have done in CO322 with ALMA this map. In gray you have the velocity 0 systemic. In blue and red you have the blue gas coming towards you and red recessing. Low resolution with higher resolution and even higher. You see how collimated is this molecular outflow. It's really like a thin needle. Another characteristic is that it is precessing, because here you begin blue and then red and blue. That is, the gas is precessing. It is almost in the plane of the sky, so it's precessing only by 10 degrees. It's sufficient to reverse the sense of approaching or receding side, and you see a blue-red and red-blue here. And in the dispersion also it's very visible. So it's a very small molecular jet, maybe 100 parsec, but what the surprise is that we don't see the radio jet. And the radio jet is certainly the cause of this molecular outflow, but maybe it's gone because the radio jet is an ionized particle, a plasma, which is going at almost relativistic speed, and after a while it disappears, while the molecular is going at 100 kiloparsec, 100 kilometers per second, and 200, and then it's still there, while in the VLA we see only the core and we don't see anymore the radio jet. So what we think is the radio jet, even if we don't see it, it is because of the collimation. What makes the collimation? In fact, it is the magnetic field which is around the accretion disk of a black hole. It is rotating so fast that you have a dynamo. In fact, you amplify the magnetic field, we can be 10 to the 12 Gauss. And then you have a mirror effect. You have all these magnetic lines that make a mirror and constrain the charged particle to be exactly in this. So this works for charged particles, so for the radio jet. For the molecules, it doesn't work because you have no coupling molecules and magnetic field. So you need first a radio jet and then untrain the molecules. Even if the radio jet is not there, you need that to make the molecular jet. And it is also precessing, so we have tried to model this precession. And for that, we take the model of microquasar, which is in our own galaxy. Microquasar is like a quasar in miniature, a small black hole, which is a stellar mass black hole, a well-known SS433, and it is precessing. It is precessing, and it is easy to see because of the scale. In fact, the scale of stellar mass black hole, you have a variability which is very short, days, months, while for a big nucleus of galaxies, you have years and 50 years and so on. So here, we don't see the thing varying, while we see it varying in the miniature microquasar. So we find exactly the same kind of model, and indeed, it corresponds to the ALMA observation of the molecular jet. So we can have in galaxies this jet due to the radio jet here, and molecular gas entrained, and you can have both, in fact. Even if you are not Eddington, you can have a dust, which is here, which can be entrained by the radiation pressure on dust, which is more easy to have than radiation pressure on the ionized gas, because the cross-section is different. So we have seen in some galaxies these two kinds of feedback. Now, at the end, I will just describe the molecular torus discovery. And again, I take this example because it's a really clear example that we have already seen. You have this nuclear spiral, and as you have seen, there's a different major axis, orientation of major axis inside the nuclear spiral. So we see other example of this. For instance, this galaxy, 1672, you see with HST is almost face-on disk with a lot of dust in one side. But when you look at 10 parsec scale, you see an edge-on disk, edge-on molecular torus. So not at all the same orientation. And this has a big velocity gradient. So since you are in the sphere of influence of the black hole, you can even use CO to measure the mass of the black hole. And this can give you, while it was not possible to do that in optical. Here another one, very well known, 1365. This one, you have the molecular torus, which is face-on, and there is a little hole inside. So inside it is first the inner Lindblad resonance here. You see the dust making a pseudo ring here. You see the CO222, and inside this, you have this molecular torus. So we have found in these first cycles of IRAM, we have 8 galaxies, and 7 out of 8 have a molecular torus. Sizes of 10 to 20 parsec, it depends on the mass of the black hole. You have masses of molecules in the disk of the order of 10 to the 7. So just to give you an idea of the mass and the importance of this molecular torus. And of course, we want to know, this is the molecular torus, is the last molecules before the BLR and the accretion disk. So we think that we'll have this kind of decoupling of this from the large scale to small. And I've put here what can happen when you have not a lot of viscosity, that is a split, the tearing of the disk. And this is very interesting because when you have several rings that are decoupled, then they precess differently because there is a differential precession with radius, and then they will collide. All these rings will collide and will lose angular momentum and will precipitate the gas to the center. So in another way to feed even more rapidly the AGN. So this is due, this precessing effect is always due to the black hole spin that I described, that torques the gas, which is accreted with a different angular momentum. So this, we see this in many galaxies. I've already shown this prototype example of the maser of H2O. You have also in 1068, you see by Gallimore et al. This red shifted and blue shifted disk, which is warped also. And when it has been modelized by Martin et al. And also for 1068 by Caproni, you see that at large scale you have this jet which is precessing also. It's not very regular. In 1068 you have this and this precessing rate. And the advantage of doing this model is that you can quantify the time scale of the alignment, which is of the order of 10 to the 4 year. It's a very small scale in the variability. So the gas will be aligned like this in 10 to the 4 years. Now, are we surprised to see this misalignment? Not at all, in fact, because this is well known for a long time that you see in this galaxy the H-alpha spiral structure, normal spiral structure, and you see in blue the radio jet. The radio jet, instead of being straight, it encounters the plane of the galaxy and it is deflected. So this means that indeed, since the jet is perpendicular to the accretion disk is perpendicular to the main disk. So it's really misaligned. You have also an example in the Milky Way. The Milky Way, we see it edge-on. And when you look at the VLA, you see this mini spiral. And you have also the ring at the inner limb-breadth resonance that you see in orange by the HCN molecule. And all this looks like more face-on than the edge-on. So you see that even in our galaxy, there is a decoupled molecular torus here. And in 1068 is really very, very complex. There has been a lot of debate, in fact. There has been maybe some gas accreted at some point, which is in counter rotation. And it is possible, since the disks are very thin, when you have a giant molecular cloud coming from a different orientation, that it can come counter-rotating. And that's what is seen here. You see at 140 parsec, you have a rotation red and blue. And when you look at 5 parsec, you have blue and red, so rotating the other way around. And when you look at 1 parsec, the major disk, it is coming back to blue and red. So in between, you have maybe accreted some gas that was in counter-rotation. So it's randomly oriented, and we have not to be surprised to have this misorientation. And this, I just described this counter-rotation here, blue, red, and so on. So is it also found in simulation? Yes. This is a simulation of our Milky Way, which is barred. At some point, the gas is going to the center and is fragmented, making stars. And the stars have supernovae, so they make some gas fountain effect. And when the fountain gas is coming back to the galaxy, it is coming in the polar ring. You see something perpendicular in the face-on view. In the edge-on view, you see a face-on this, so it's the gas can come back in any orientation. In this particular case, it was a polar ring. So you see that we are not surprised to see the misalignment of this kind of disk in the Milky Way when you see this simulation. So finally, I will summarize what we have gained by going in radio astronomy to high resolution, and especially with ALMA. We have found that the fueling is due to small bars within bars and maybe a nuclear spiral, which is a 10 parsec scale. Now it's more clear the way that we can feed the nucleus. The feedback also, we see some outflows that are due to radio jets, and maybe some also radiation pressure on dust. And finally, we have discovered these molecular tori, which are decoupled from the rest of the galaxy, and which replace, in fact, the paradigm of dusty tori. And the dust is, the obscuration is due to the polar cone. But here we have accretion different dynamical time scales, so it's explainable. And maybe there is a way to reach to the spin of the black hole at the smaller scale. So thank you very much.
Thank you, Françoise. So questions?
So when the black hole spin applies the torque on the accretion disk, is that because the spin is misaligned with the accretion disk, or the effect of the spin is perpendicular to it?
Well, in fact, yes, we think that the gas arriving has no reason to have the same angular momentum as this black hole spin. So it arrives with a different angular momentum, and then the torque is due to the fact that the gas is obliged to follow the referential frame, which is rotating with the black hole spin. And then there is a torque here, because the gas has to be aligned with the black hole spin. So this torque is due to that. So you are warping that, and that is making different orientation that we see in the center. Yeah.
Okay, other questions? I have a question for you. I mean, a lot of what you've shown tonight is about the combination of observations at different wavelengths and so on, and we have plans in the centimeter. If we were upgrading ALMA 10 years from now, what would you like to see?
Yes, a very good question. I've heard that there are plans to have more sensitivity with ALMA, either by going to a wide band and also having at long baseline more antenna. That would be nice.
More sensitivity on
more sensitivity, because when we go, it's possible to go to higher resolution than 30 milliseconds, but then we lose sensitivity. So we cannot go further, but we would like to go further, and the sensitivity is a must for that.
Okay. Other questions?
I guess I have a question, which is when discussing the bars and the sort of, you're talking about like the structure of the stars going around it and the surrounding gas. Does that analysis involve any sort of involvement with dark matter, or is that at a scale where that's not really relevant?
Yes, you're right. The dark matter is not relevant there, because we know in the center where we are in 100 parsec, 10 parsec scale. And of course, the CDM simulation predict a cusp of, but the cusp is 1 kiloparsec, sorry. And in fact, what we see with the rotation of spiral galaxy, we see a core that is a plateau of density. We don't see a cusp. So the density of dark matter is negligible in this zone. So it's only gas and stars with that potential.
Okay, any more? If not, I'd like to thank all of you for coming to the lecture, and let us thank Françoise one more time.